Yeah. I just have my own Zoom, so I'll send the video later. Yeah. Okay. Hi, everybody. Wait for the stragglers.
Come on, birthday boy.
Birthday boy. Come on,
Okay. Good morning. Today we're going to talk about what comes next. So how to make your model better. So where we're at right now, you're all training. That's very exciting. Congratulations. It's a big step. You probably have a bunch of plots like these. You may or may not know what to do with them. So we're going to talk about that. You also have results. So you've got some kind of accuracy metrics set up. You know what your accuracy is on different classes. You might be wondering, how do you improve this? You've been inspecting your data to try to figure out how to systematically improve it, to address some of those lower metrics maybe, or just to understand your problem better. And so once you've done all that, where do you go? How do you improve the model? That's what we're going to talk about today. So what we suggested so far is really trying to emphasize, get to know your data. Understand what it looks like, understand your labels, understand what your model's doing on the data. Just try to get a better, scientific understanding of what's going wrong or what's doing well. After that, you can iterate on your data. It's always going to be the most effective thing to do to improve your performance. Iterate on your data set, maybe iterate on your model. That's what we keep telling you. We really believe it. If you read computer vision papers, you get the complete opposite perspective from, or at least you get the impression that we do the opposite thing, which is we develop a super fancy model, we get the perfect settings, and we get, the state-of-the-art accuracy. And what we're trying to get through all of your heads is that actually the path to enlightenment comes back to your data. So you start not really knowing anything about the model, you just try to make your data good. Then maybe you start reading computer vision papers and you think that you need a contrastive design to pre-train image text encoder foundation models jointly with contrastive loss, yada, yada. This is actually in the abstract for the current state-of-the-art model on ImageNet right now. That's like 0.01% better than the next best thing. Eventually you realize that the most effective way to make progress is just to actually make your data good. And so we're going to kind of compromise today and talk about, assuming that you have done everything you can to make sure your data is correct, you're iterating on your data set, you're constantly improving it. What else can you do to actually improve the settings of your model? And what are the principled ways forward? And hopefully what that's going to result in is getting a reasonable improvement in performance. It's not going to be game changing, although sometimes it can be large, and so we'll kind of get to that. So what that involves, first we're going to talk about these graphs that you're seeing when you're training your neural network. So looking at the training and validation curves during training and deciding what that means for your model and how to use those curves to identify problems and select your best model. Some of that's going to be review, some of it may be new. Then we're going to talk about hyperparameters. So we've told you to kind of disregard them for the most part up until now. But in this lecture, we're going to talk about principled ways to select the best ones, to identify which ones actually matter for you, and how to be efficient in getting decent settings that are going to give you pretty good performance. And then bonus section at the end, we're going to address one particular very common problem, which is imbalanced data. And we're going to talk about a few ways that you can try to address that. Okay, so first we're going to talk about training curves. So if you used some, off-the-shelf code base, or maybe you integrated with Comet, now you have these plots. And we've kind of gone over a few different things that you can pull from these. We're going to be a little more explicit about it now. So just to recap, like usually you have a plot for your training set and you have a plot for your validation set. So we use these for different things. The training set is what you are actually fitting your model parameters to, but the validation set is helping you validate that the fit that you have for your model actually generalizes to data outside the training set. And what we're going to see is that you also should use this to select your hyperparameters and to know when to stop training. And so the reason we use a validation set is because of overfitting. So if you have, this is like a toy example where the true data distribution is like a parabola roughly. And so you're sampling from this true data distribution, you're trying to fit a model to the data, and this model is just a line fit. So essentially you're trying to find a good fit of your training data that still provides a good fit for your validation data. That would be generalization. Okay, so if you keep trying to minimize your training error forever, you get to something like this. This would be overfitting. So now your training error is 0, but your validation error is massive. And so this is, this is a toy example of what we're trying to do by plotting training and validation curves during training, is try to find the point where you're kind of about here. Because if you keep training forever, you're going to get here. Okay. So how do we measure fit? How do we measure the goodness? We can't just use a distance function like in this last graph. We usually have either performance metrics. So these are things that you've already sort of implemented or been working with, things like error or accuracy, which depending on the task you're working on can be defined in different ways. This might not actually be accuracy. It might be something like mean average precision. You can also have loss functions. So a loss function is sort of an error metric that is differentiable, that's interpretable by the model. And so you compute a loss that's sort of like an error in a form that the model can use to optimize. Okay, so deciding whether or not you should focus on loss or error or accuracy while you're training is kind of dependent on your problem. So a lot of the time you can sort of decide what is the most important metric for my task. And I think that's what a lot of people have been thinking about this last week. So if you're doing object detection, it might be mean average precision. So then during training, what you want to look at is the validation mean average precision. Does that make sense? Cool. Any questions so far? Okay. So now we're going to go through a few common situations that you might see during training. So first, if you just look at your training loss, you're probably going to see that it's going down, and it's going to go down for a long time. This doesn't actually tell you whether or not you have a good fit. This tells you that you are fitting to your training data, which is a good first step, and it's a good sanity check. If you can't fit to your training set, you have a problem, because this is the exact data that you're showing your model that you're optimizing a fit for. So if this isn't going down, you probably have a problem with your data or your model. But if it is going down, you don't really know anything yet. If this is happening where your training loss is going down, but your validation loss is staying the same, something is fishy. So this doesn't necessarily mean something is wrong, but it probably does. So check your data, make sure that it's all formatted correctly, visualize your validation set, make sure the ground truth labels are what you expect, and check your training command for errors. So there are situations where this could happen, where maybe you just have a very tough validation set, but it's pretty rare. Okay, the more common case is that they start kind of going down together. So let's say you ran a training run, and this is the graph that you have at the end. You notice that the loss for both train and val are still going down at the end of training. So that means that you could keep getting better if you train for longer. And so in this situation, add more epochs to your training schedule, keep training, try to get that validation error to get as far down as you can. Okay. So once you've done this, okay, now it's sort of flattened out. That's great. You still notice that there's going to be a difference between your training loss and your validation loss, most likely. This is kind of to be expected. So the training data is actually what you're showing your model. To some degree, it can memorize that data. And so there's going to be some generalization gap to the validation data because it's never seen that imagery. But this is something that we can reduce, this gap. And so that's going to be covered partly the rest of this lecture and also in Bjorn and Tarun's lecture on Fridays, how to improve generalization performance using different training techniques. So the other common pattern is that you're training, you reach some minimum of validation loss, and then the model starts getting worse on your validation set while it's getting better on your training set. So this is essentially that overfitting case that we saw before. Your training error is getting better and better and better because you're overfitting to the training set. So your generalization is worse, your validation performance is getting worse. And so really what you want to do is stop your model right at the minimum validation performance. Yep. Yeah, exactly. So that'd be the beginning of overfitting to the training set, which in that toy example looks like creating some crazy interpolation of all of them. Yeah, Mark.
Actually, like whether more people at the beginning and then see where it's better out.
Exactly. Exactly. Yeah. So the question is, should you just start with a long training schedule, see how long it takes to flatten out or hit the minimum, and then kind of use that moving forward? Yeah, that's something you should do.
Good, so there's just like caveat there, it depends on what learning rate schedule you're using. If by default it's something like a cosine learning rate, then it's basically just, it will stretch out what the actual learning rate stat value is over the number of epochs you specify.
Yeah, that's
So
true.
then if you just say train for longer, it might actually do the same thing, just moving slower. So that general rule of thumb only works if you're using sort of like some sort of fixed learning rate schedule.
Yeah, that's true. So if you like, the easiest thing to do is just start with a constant learning rate that never changes, because then you can actually like interpret these curves and make some decisions based on that. It gets more complicated if you have something like Sarah's saying, like a cosine learning rate decay schedule, which means over time you're reducing your learning rate, and often that is scaled, like the rate of decreasing the learning rate is scaled to the total number of epochs. And so it's a bit hard to tune the length of training in that case. And so if you can, I'd recommend kind of like leaving that for later, start with a constant learning rate, and then come back to these more complex schedules. Chris?
You train to the minimum point, like just go back to my spot where
Yeah, you can. Yeah, exactly. Yeah, that's what I was going to say. So you don't have to just time this perfectly, get your epochs perfectly right so it stops at the minimum. Actually, you can save a checkpoint of your model every epoch. And then you can go back and look at this graph and you can select the model that was the best.
Some of these repositories by nature essentially keep like a best.pt that just tracks performance of val over time, and then that'll update if one of them performs better on your validation set on some given metric. Now you need to check like what metric are they using to decide what's best, and like does that align with this? But so there's sometimes the way to do this is actually you can just do it automatically. Let's keep track of which one performs best and save that one that's best and post it whenever it's better. And then you just always use best stuff into.
Yeah, so YOLO V8 does that for anybody using YOLO. The CT classifier repo does not do this, but it does save a checkpoint after every epoch. So you're going to have to either manually go back and see what your best epoch was and then use that as your model moving forward. Or you could code up basically a version of what YOLO does, which is you keep some running like best value. Every epoch you check if your new model is better than that value. And if it is, save it as like best model.pt. Does this make sense? Best is the best on the validation set. Exactly. According to some metric. Yeah.
You don't just usually inspect it.
Yeah.
Is that it?
Yeah, that's a
We
totally,
just think that's black, but
that's a valid way to do it. I mean, you're gonna get the exact number anyway if you're sort of mousing over that graph. And so that's kind of the manual way to do it. And then if you wanted to make it more exact, you could implement it in code. But yeah, like Sarah said, it's metric dependent. So whether or not you should use validation loss to pick your best model, or you should use validation accuracy or validation average precision, you kind of have to decide that based on your problem and what you think best captures what you're trying to do.
so the loss will be, that's an unbalanced metric. So the very best thing on this loss curve could be if you have a really unbalanced data set, the model that just predicts the common class all the time. So like, yeah, like there's a bit of nuance here, but the nice thing is if you just save all the checkpoints, then you can run different evaluation metrics. You do your offline eval for the one at the end and the one that your metric said, the loss says is the best one, and see like what does this change for these different other things on this point. So model selection can be more complex than this. But the point is that you can actually, if you just save off checkpoints, you can think about selecting the best one, and it might not be the last.
So we've been talking about like when you have class imbalance, if you just compute accuracy, that might not actually capture what's going on. If you have like a 10-to-1 imbalance and you have a 90% accuracy, you might just be predicting the one class. And so maybe you want to use a balanced accuracy actually to check which model is best for you. Okay. So these are the main cases. This is the key takeaway. Use your validation performance to understand what's working and select your model, and use early stopping. You should have some way to go back and pick your best model, and you should never just be stuck with the last one because it's probably not actually the optimal one. Okay, if there's no more questions, that's all I have for training curves. Go ahead, Kara.
If it plateaus, is
Yeah.
that a sign of something, or is that more looking like accuracy?
Yeah, if it plateaus, I mean, if it truly plateaus, then that probably means you've sort of found the minimum of the curve. But usually you could try maybe like a higher learning rate and try to get it to go down further or train for longer and make sure it actually has plateaued. Like sometimes it'll plateau for a bit and then start going down again. In that case, you can also reduce the learning rate. Kind of an additional trick that would fall under like learning rate scheduling is that once you start to plateau, people will reduce the learning rate because now you've gotten to some like local minima potentially. But smaller movements will kind of get you to better performance, if that makes sense. Yeah. Would you agree with this for plateau?
And you can chat about it more when you have that picture.
Yeah. We have a slide on learning rate, so talk about that. Okay. So hyperparameters. What is a hyperparameter? Hyperparameter in general is a parameter that you have selected, not learned. So your model is a neural network that has millions of parameters that it's learning every iteration from your training data. Outside of that process, there are other parameters that you set, like how big is your model? What's your image size? What's your confidence threshold? What's your batch size? These are hyperparameters. They're not learned, you set them. How do you set good values? Is the question we're going to try to answer. Typically, where you find hyperparameters are in config files. So if you're using CT classifier or you're using YOLO or you're using some other library, there's probably some YAML files or CSV files or something where these hyperparameters are stored. Sometimes in less developed code bases, they're just hard-coded into the code, which is suboptimal because you have to make code changes to try different values. Ideally, you keep any hyperparameters that you might change in a config file, and then you save a new config file for each new hyperparameter configuration so that you can quantitatively compare different settings, right? So in the CT classifier repository, there's a few, they're commented as training hyperparameters. So you have image size, This is something that you could change and see how the model does after you change it. Number of epochs, batch size, learning rate, weight decay. These are all hyperparameters.
Would you then recommend that making a new a file for each
I would.
rather than change one?
So it depends. You need to have a record of what you did. So if you change that config file, git commit and name it what the experiment was, then you can always come back and like find the one that did the best. But I like to copy it, name it something significant for the experiment, like change like learning rate lower or something, learning rate 0.01.
Change.
Exactly.
I actually have a very strong opinion about this,
Yeah.
which is like, just in case, because I've had this before, where you think you use some naming convention that's really clear and you realize it isn't. I always have, and I think both of these repos maybe or maybe don't do this, make sure they do. When you launch a model, you save the config in the folder where you were saving the checkpoints. So you always have the config that matches those checkpoints directly together. And then you'll save yourself a world of hurt. Yeah, I just copy it to that folder and that's like I just got burned this way a couple times. This is my solution.
Yeah, and actually both the CT classifier code base and YOLO do this automatically, which is nice. Other code bases you'll have to check and maybe implement that yourself. Bjorn, did you have a question? Stretch it. Okay. Question? You guys have a question or good? Okay, cool. Okay, so this is going to be a long list of common hyperparameters. This is so you can kind of identify them when you see them. So some model settings would be like the backbone that you use, could be a ResNet or an Inception or something like that. The model size, so usually different architectures have different settings for how many layers. Like a ResNet 50 has 50 layers. A ResNet 101 has 101 layers. This is something that you can change and see how it changes your performance. Your model pre-training settings. So you might be starting with just a from scratch random initialization of the model. In practice, it's almost always better to start with a model that's been pre-trained on some large data set beforehand, like ImageNet or Coco. So many code bases just have this implemented by default. You'll download like the YOLO V8 weights that were pre-trained on Coco. So it gives you a pretty good starting point. Image size is another one. Confidence threshold is another one. The number of training epochs, the learning rate and the learning rate schedule, the batch size, the optimizer. Okay, we're going to go over a few of these in more detail, but these are just things that you should be aware of when you're reading through code, that each of these is a choice. And the best choice for somebody else's problem is maybe not the best choice for your problem. Also, some of them only apply to training. So you have training hyperparameters, and then you have other hyperparameters that are valid for both training and inference. So you just need to kind of be aware of which ones are being used by your model and where they're being used. And once you deploy your model, do you need to keep any of these in mind? So confidence threshold is a good example of that, where you don't really use the confidence threshold during training, but you will use it during inference. So we'll come back to that in a second. Then you might also have task-specific hyperparameters that other people don't see in their code bases. So like for object detection, you have something called a non-maximum suppression threshold. This is really only used in detection scenarios. So if you're running a classifier, you don't need to know what it is. Segmentation, you might be doing some downsampling of your masks. In object tracking, you might have a parameter for like the minimum valid track length. So which ones do you filter out if they're too short? Suzanne? Yeah, I was gonna, it's okay. maybe we can have a side conversation about what non-max suppression is doing. I didn't want to spend too much time on it, but essentially, when you have an object detector, it's going to predict thousands of boxes per image. Okay, they're quite naive on purpose. YOLO predicts 108,000-ish boxes per image every time. Okay, most of those will cluster around the objects of interest. So you might have 1,000 boxes on top of your animal that you're looking for, but you don't want to predict it 1,000 times. So non-max suppression is the algorithm used to select one box out of those 1,000 that's representative. Thank you. I think I've explained it like 10 times. So there's a threshold for that. You have some overlap threshold, right? Like you might want to get rid of any boxes that overlap at all. You might only want to get rid of them if the boxes are really, really on top of each other. This kind of depends on your data. Like if you have really sparse data with only one animal per image, you can choose a pretty low threshold because you know that you're only going to have like one box per image and you want to get rid of the rest. But if you have like herds of animals, they might be really close together. And so it's more sensitive to eliminating those boxes. You might end up with false negatives. Yeah, if anybody wants to talk about it more, we can talk about it after the lecture also. We can have a object detection mini lecture. So when do they matter? We've been telling you to really focus on your data. That's the most effective way to move forward, but sometimes these hyperparameters do matter. They can have a large effect on your model performance, even if you just stick with the defaults. Sometimes those defaults are suboptimal for your problem. When you start with a big code base like YOLO, they publish a paper that says they're the best object detector on the COCO dataset. The way that they got that performance is they tuned their hyperparameters specifically for the COCO dataset, which has a bunch of people and cars and bikes in cities for the most part. It doesn't look like camera trap images, and their settings are probably suboptimal for you. Okay, some of them work well, but some of them don't. And so the key is like, how do you identify which ones are going to impact you? This is not a trivial process. If you wanted to find the absolute best parameters for you, you would have to do a massive search over the hyperparameter space, spend a bunch of time and money that otherwise you're not spending improving your data and understanding your problem. Okay, so the main takeaway that we're going to try to get across here is that you should try to be effective with your choices and try to reduce the number of parameters that you look at so that you can focus on your real problem. Okay, but we need to select decent first values because you can cause pretty bad model failures if you have bad parameters to start with. And I'm going to give a couple examples from my group, starting with Kara, who was lied to by the YOLO default commands. So I'm calling these horror parameters. They're horror hyperparameters. If you look at the YOLO default commands, it will tell you to train with an image size of 640 and evaluate with an image size of 320. And so Kara followed the guide perfectly, and she found that in her images, this chickadee was not being detected, even though it's pretty obvious. This is actually a pretty common pitfall. So misaligned training and inference hyperparameters. A lot of the time, if you have a hyperparameter that's used at both training time and inference time, you should keep it the same. Okay, so once we fix this, changed it to 640 for both, now the model perfectly detects this chickadee with almost a 0.4 score. So keep an eye out for stuff like that. Next horror parameter example is Martin's data. So Martin had this problem where all of his ground truth segmentations looked really wiggly. This should be like a smooth mask that covers the object, but it almost looks like stairs, right? So this was happening during training with his ground truth. This is also what his predictions looked like. Okay, and if you dive into the YOLO repository, you see this config file of a bajillion different settings. Okay, and it turns out that down toward the bottom was this mask ratio. And if you read the comment, it says mask downsample ratio during segmentation training. So this was a parameter that they clearly set because in the COCO data set, you have big cars, big people, big bikes. You don't need like this pixel by pixel perfect segmentation to get them right. But in Martin's data, that's not true. So in COCO, they were downsampling the resolution of their masks by 4 because you would still roughly get the same object enclosed. But in Martin's data, it looks like a weird step function. Okay, so lucky for Martin, the solution to this is just to get older. Today's his birthday. Happy birthday to you. Happy birthday to you. Happy birthday, dear Martin. Happy birthday to you. Yeah. Okay, I think the bad news is that we haven't actually solved it yet, but today's the day. Okay, so maybe this is scary now because I've told you there's a bajillion hyperparameters. It takes a lot of effort to tune them, but they can really screw up your data. Okay. It's not that scary actually, because you can really follow the 80-20 principle. 20% of the effort is going to get you 80% of the results. It's worth the effort to get these pretty good, but there's huge diminishing returns at getting them perfect. Okay, so we're going to give you a few, principled ways to get pretty decent values on your data. And something to also consider is that any time that you spend on this is not spent improving your data, understanding your model, understanding your problem. If you spend a bunch of time getting, a boost in 2% accuracy, that's a boost in 2% accuracy on your validation set, which we all know is not perfectly representative of data that we might see in the future, and that might just be wasted effort. Like getting pretty good is probably going to get you pretty good. Okay. So here are the principles. First, reduce your search space. You don't have to search every possible value for every hyperparameter. You can start with reasonable values that are informed by your domain knowledge. Okay. So I put a note, did we mention you should look at your data because we told you that a lot of times. So things like the non-max suppression threshold. If you know that your objects are sparse, you don't need to pick some super high non-max suppression threshold. You can start with a lower default. Okay. Always make decisions based on the validation set performance. I think we went over that in pretty good detail, but just because something gets you better training performance doesn't mean anything. And you should keep, when you change these hyperparameters, use the same methodology, look at your training and validation curves, use early stopping, pick the best model. Okay, that's how you know what the best possible performance for each hyperparameter setting is. And then avoid common pitfalls when you can. These can be hard to know about until you've encountered them, but we'll give some, very basic common ones. The image size one is huge.
The image size one, there's a couple where if in the config, the thing is specified for training and tests separately, then it is going to be so easy to forget and change it for train and not for test. So just like, those are the kind of things, that's the common pitfalls. Like, don't forget that some of these parameters need to be changed in 2 places in your config.
Yeah.
Yeah. Settings in the config file.
So it turns out that for some special cases, so for some object detectors, for example, you can train efficiently on smaller data, but actually they're technically with a batch size of 1, input image size somewhat agnostic. And so there are some tricks where for COCO, you train on downsampled images, then you actually test on the full resolution images and you get better. So the reason that is a thing is because for some object detection models on some data sets, you get that computer vision paper better performance by testing on the full size image, which might be much larger than your training images. But then as a result, you end up with this thing where for a lot of other cases, that's not true, and now you end up making a mistake in that setting.
Any other questions before we move on? Because it's about to get very opinionated. Okay, we're gonna go through a few common hyperparameters and just give you some hard and fast rules, what's worked best for us. Other people might disagree with these opinions, but I think it'll get you pretty far. Okay, batch size. Usually this doesn't affect your performance within some range of values. Okay, if you have really small batch size or really large batch size, where small is like 4 images and large is like thousands, you might see some performance difference, but you're probably not going to see that much difference between like training with 16 or training with 32. The batch size is just how many images are processed by your model at one time. Okay, then you compute a loss over the batch, and then you take a step in the direction of learning according to the loss on that batch. Okay, so intuitively, if you have a very large batch, like 1,000 images, you've got a really good average direction that you need your model to move in to do better. If you have a really small batch size, it's a bit noisier because you've sampled a couple random points from your data set. In practice, just try to select the largest one that you can based on your GPU memory and based on your RAM. Okay, you can check your GPU memory usage using NVIDIA SMI. I think most of you have done this by now. So what you can do is you can have 2 terminal windows open. On one of them, you launch your training, and on the other one, you look at NVIDIA SMI, and you look at how close you are to maxing out your GPU memory. You can also just keep increasing your batch size until you hit a CUDA out of memory error. That is okay. It's not a scary error. We do it all the time. You're not going to break anything. Just see how high you can get. Okay, the caveat on the clusters is that 4 or 5 of us are all sharing the same machine that has about 96 gigs of RAM. So divide 96 by the number of people in your group. That's how much RAM you're allowed to use. Okay, we all have to share. You can use this top command. These slides will be accessible also, so you can come back and reference this. Top-B-N1-U, your username will show you how much memory you're using. So it'll show you all the processes that you've launched, and you can just add up the percentages and see, are you using more than like 16 or 20 gigs of memory that's been allotted to you? Okay, so that's the basics of batch size. For the most part, it's not going to affect your performance too much, but it does interact with learning rate and image size and model size. Okay, those are all things that, so batch size and learning rate are very tied because you're going to take a learning rate step according to the gradients on your batch. Okay, it's also tied with image size and model size for this memory usage, because all of those can affect how much memory you're using. Yeah, fair. That's a great question. I don't know. It seems like it might. Does anybody have an answer for that? Yeah.
Essentially, then you're just not doing stochastic gradient descent.
You're just doing gradient descent. Yeah. You could try both. So the advantage of the smaller batch would be actually getting a bit more noise in there. Adding a bit of like randomness and regularization can help you get over like local minima in the loss space.
But if you can actually do the batch with your full data set,
Should you?
maybe actually you could explore that randomness by just running multiple runs with different random seeds, because that's basically setting the ball at different points in the graph initially and seeing where it rolls down. And the reason for stochastic gradient descent is if your data is too big, you have to do something. Like you can't do all of it. Most computer vision data sets we work with, I would not have that option. I don't know, actually, that's a very interesting question. Let us know.
Yeah. Yeah.
You can still have stochastic descent though, just across efforts. Right? You can have your entire data set in one batch. And then just like each effort to stochastic. But anyways.
How do you mean moving around the optimization?
Like you're optimizing and stochastically descending the loss.
Uh-huh.
But your learning rate isn't in each one.
Right. Okay. Cool. Good question. Okay, so hopefully, oh, sorry, Jess. Yeah. Yeah. So that's another hyperparameter that you can try. I didn't actually put a slide for optimizer. In general, if you want to try different optimizers, try SGD, try Atom, maybe try RMS prop. I don't know. I would try those two and see what happens. That's one that you can't really be principled about. I think you just have to try it empirically and see. Did you have a comment? Okay. Okay, next is the learning rate. So I kind of described this briefly. I think it's been described briefly in other slides, but the learning rate is essentially how big a step you take once you know the gradient with respect to your loss. Okay, so you know how much loss you have on your batch, you know which direction you should go to get better, to get a lower loss. Learning rate is how far you go in that direction. So if it's too small, it'll take you forever to converge, and you might wind up at some local minima that you can't get out of because your step size is so small. If it's too big, you can overshoot the minimum, right? So the minimum loss here is kind of the bottom of this parabola. You're trying to get all the way to the bottom. So if you have the perfect learning rate, you'll eventually get there. If your learning rate's too big, you'll jump back and forth, and you'll never get to your best loss. So in practice, I usually just try 3 different orders of magnitude to start. So take the default, divide it by 10, take the default, multiply by 10, try those 3 learning rates and see what happens. Usually it will be pretty apparent early on in training which one is doing the best. You don't necessarily have to train all the way to the end to know this. Okay. Once you've got kind of the best one out of those 3, take that one, divide it by 3 and multiply it by 3 and try those options. Okay. And see if that helps you fine tune it any better. Okay. Outside of this, I wouldn't mess with the learning rate. Just try to get a decent value. The order of magnitude thing is going to get you pretty close probably.
Actually here, just in terms of like, that's your starting learning rate. And then the other thing that you can do is this, like, once the training looks like it's saturated, a very, very common trick is you drop the learning rate by an order of magnitude. And what you'll see is the model forms a little whoop, and then maybe do it again, and it's whoop, and like, again, diminishing. But the reason for that, this is a very fun thing, is see this? If this is like your minimum. So what you're doing is like, the model's like taking some steps. So maybe let's just imagine this is a problem. So if I'm here and I'm saying my step length is like now going to be some amount of space on this axis. So like if I start here and then I take a step, maybe it'll take me here, like it's in this direction. So what you do is you say, okay, I want to take a step in this direction. So you go down to this axis, see where it is, and you come up, and you're like, all right, now this is my new thing. Then you go down, you come up. So maybe if you're here and if you're learning, if your step rate is too big, you can end up in this weird thing where you go, okay, I need to, the gradient's in this direction. So I need to go over here, and then you go whoop, and then you come up. And like, all right, the gradient's in this direction, and then you go whoop, and you come up. And so you end up in this like weird thing where you actually, your learning rate is it's too big. So you can't get any further down because you keep like missing it. And so then when you drop the learning rate, you can now make more progress towards the action. Anyway, yeah.
How do you profit wise running?
So you're saving checkpoints. So you either can set what's called a step learning rate schedule in your actual config, where you say, do this learning rate until this step, and then this learning rate, and after that step until the next step, and then this learning rate. That's an option in what to do. Or you can basically train it until it's accurate, realize like, I might want to change my learning rate. And then at that point, now basically add to your config, now drop the learning rate at this step. And then keep going.
So on this graph, it's the learning rate dynamic. You mentioned that we should put the constant.
So what we're talking about is basically a manually specified learning rate schedule. Where it's a constant learning rate until training saturates, until you're not seeing any performance improvement. And then you're setting a now order of magnitude lower, but still constant learning rate. This is a trick that is very interpretable and very easy to work with and really helps you get in the right ballpark of these numbers. Now, there are a lot of much fancier learning rate schedules that actually do like automatic slow decay of learning rates.
So this would be the.
So that I think here, maybe there's some sort of like represented automatic slow decay of learning rates where as you're getting, your model's getting better, it's automatically adjusting learning rates smaller. And those actually often do, again, maybe get you a slight better performance, but they can be very difficult to, when you're trying to figure out what should the starting value and the end value for that cosine learning rate decay or whatever be, trying to figure those things out when the number of epochs you do is directly related to the sizes and everything, it can be very difficult to get a ballpark. So when you're trying to just figure out what is roughly the right ballpark to start in for that, the start of that thing, then doing these constant learning rates is much more interpretable and much, I would say, a much better way to start doing that for persuasion.
So would you start with?
Yeah, so when I say try these different settings, I mean try those as a constant learning rate and run training and see what your final performance is. Learning rate schedules, like what we're talking about, automatically decaying it over time, that can definitely help, but it can be hard to figure out. Basically, it interacts with all your other training hyperparameters too. And so generally I try to get like a pretty good constant one, then set all the rest of the parameters, and then try to, you know, modify the learning rate schedule later with like an automatic decrease or like a cosine decay or something like that. Sure.
You want me to write functions with an object in package called a learning rate scheduler, where you can choose type of schedule, you can choose how many wait before change your schedule, and you can even choose what method to look at. You can do this on the validation of start. It's not something you need to do.
Yeah, the key really is just only change one thing at a time. So try to get a good constant learning rate as a starting point, and then maybe try adding in a schedule after that. But don't change everything all at once, or you're never going to know what was the cause of the difference in performance. Cool. Yeah.
I set the learning rate and I don't have a scheduler, I'm just gonna use that, right?
Yeah.
And then later, if I had a scheduler, it's smart enough to know, like, immediate set a learning rate as a constant scheduler to take over and kind of do its thing. Like, do I have to?
No, you'll have to modify something. So, so typically, like if you just have LR equals 0.01, now your learning rate's a constant.
Yeah.
Okay, you can then create instead a learning rate scheduler object, give it some parameters, and now every iteration you ask what the learning rate is.
Okay.
So the learning rate just changes every iteration.
But like Sheer said, all of this sort of implemented, there's examples of how to set these in the config. Like it's something you set in the config, it's just now your learning rate is a single thing. It's like learning rate is whatever, and then there's like some set of parameters now for the learning rate schedule.
Oh, okay, so those are the parameters that could be set into, often the scheduler.
Yes.
Yeah.
Yeah. So I think this kind of actually falls into that same thing of like, there are so many newer and best and bigger, whatever architectures. But in terms of like, I have never personally experienced like changing a learning rate schedule and having it change my performance by 20%, right? It's like, we're talking small differences. And it's again, just a whole other can of worms. And really, it can be so, I think what we're trying to give you is rules of thumb for like how to find reasonably good values to start from. And then we can start adding additional complexity, but like start with a constant learning rate, change the step manually, kind of see what ballparks you get into. Then maybe try like pretty straightforward learning rate scheduler and see if it makes a difference.
If we're saying that some of these changes are like really big small,
Mhm.
you know, like image net, oh, this is 1%, blah, blah, blah. If you're trying to make something that was useful, let's say for other people in the field or like contacts, could you pretend, and obviously like you say to your hardware, whatever. But could you potentially say like, look, this is the simplest probably give you a default assumption of, as you can see, the accuracy change or if your resource constraints, what about
That is absolutely
Yeah.
what I want you to do. That is desperately what I want you to do.
Totally.
That's
And
perfect.
a lot of people will do something like that. So like if you go to the YOLO homepage, they have these graphs that look like an arc. And what they're doing is each point on that arc is a different sized model. So they have their like nano model, they have their small model, they have their large model, and it compares like inference speed or training speed with performance. And so you can see like using the bigger model gets you better performance, but it's at the cost of some speed. So actually next week we have a more in-depth lecture on that too. Okay, I'm going to try to cover kind of a lot in 8 minutes. So all these slides will be up for reference, and we can debate the choices that we're telling you to make later. So image size is another important one. This one's kind of self-explanatory. You have to give images to your model in a specific size. So what should it be? Typically the defaults work pretty well. So for object detection, a lot of the time the default is like 680 or something. For classification, usually it's more like 200 to 250. These are just like defaults that have worked well for a lot of people. In general, increasing the image size helps with finding small objects, because in your convolutional neural network, you're sort of slowly reducing the spatial dimensions of the input over time. And so if the objects start out occupying more pixels, then deeper into the network, it will still be, you know, more than just one value to determine whether it's an object. It can also help with fine-grained features, but there are diminishing returns. So you can't just blow up your image to like 5,000 pixels and expect it to do better. And part of that is just the way that convolutional neural networks are designed. They have kernel sizes that look at like 3x3 patches of pixels or 5x5 patches of pixels at a time. Okay, and they've been pre-trained on images where like, you know, somebody's shoulder takes up a 3x3 patch. So now if you've made this person like 1,000 pixels tall, you're not going to be able to find the same edges and the same contours and stuff. So that's a bit more detail than you probably need, but just know that larger is sometimes better, but there's diminishing returns. So if you want to try larger, try increasing it by 50%, see what your performance looks like. Try doubling it, see what your performance looks like. Yeah. Yeah, yeah, it does. Yeah. Yeah, yeah, and probably, you know, you just kind of have to try it. You could visualize it. You could break down performance also by the size of your object. So often in object detection, this is done. You'll get like an average precision for small objects, average precision for medium objects, average precision for large objects. And so you can see what happens to all of those categories when you scale up your image. Usually you're going to see the small image or small objects performance go up. And whether or not there's a trade-off with the large objects will just kind of depend on your data. Yeah. And then the common pitfall here is like we talked about before. Try to make sure the objects are the same size during training and inference. So most of the time that means just make sure your images are the same size during training and inference. But if for some reason you have like different settings on your camera, like you took pictures really close up during training and really far away during testing, you might have to kind of resize it to make sure the objects that you care about are roughly the same size. If that makes sense. Okay,
When you say they're roughly the same size.
of pixels, yeah. So there's a cool paper about this. If for some reason you think your objects are different sizes in train and test, check out this paper. It's linked in the slides. It'll be in the resources folder. Okay, augmentations. Bjorn and Tarun are going to cover this tomorrow. But basically what an augmentation is you modify your input during training to increase artificially the diversity of your data. In general here, to some extent you can throw the kitchen sink at it, but you want to make sure that you're using augmentations that make sense for your data. If you're analyzing spectrograms, it doesn't make sense to rotate them 30 degrees, right? Just use common sense and use your domain knowledge to decide whether or not a given augmentation is even appropriate for you to throw in. Finally, the neural network architecture. It's really tempting to just want to use the biggest, fanciest model that just came out. But there's a lot of considerations there. So in most cases, something like a ResNet 50 is perfectly adequate. It will handle probably 90% of problems. It's what I use for most of my projects. If you're really finding that for some reason a ResNet 50 cannot represent your data well, it could be that there are not enough parameters in the model. That would be the model capacity. ResNet 50 has like 25 million parameters. Okay, and the default networks used by like YOLO are very similar kind of to ResNet 50s, at least in size. And so you can try a few different sizes and see if it improves your performance, right? But don't get carried away. Probably something that is increasing the state of the art on ImageNet by 0.1% is not going to do anything for you. So just be very wary of these like state of the art papers. Bigger, fancier models are often also more sensitive to hyperparameters. So especially transformer-based models. A lot of the most recent literature is on transformer-based models, and they show that they can get better performance. But this is with very carefully tuned hyperparameters on massive data sets, like billion image data sets. They're spending potentially millions of dollars doing hyperparameter tuning on these models. So be wary. Data hungriness is the same thing. So the transformer models need a lot of data. And then usability. A lot of the most recent, fanciest models are slow. You're not going to be able to deploy them in a cost-effective way or fit them on an edge device or whatever you might want to do. And they're also less supported in terms of code. Like YOLO and other, classification or detection code bases are quite well supported. The code bases have been worked on for the last 5 years. These new emerging research ideas are brand new. The code's hacked together. It's going to be really, really hard to actually get it working in your final system. So things to keep in mind. Just use a ResNet 50 if you can. Okay, confidence threshold. I'm going to try to wrap up quickly. So confidence threshold, this is something that's really only at inference time. You usually don't use this during training. It can be really important depending on what you're doing. So this is just, if you have a detector or something, what's the minimum score output that you consider to be a real object? Okay, and so we've talked about this trade-off between precision and recall. So any threshold that you pick, there's a trade-off. You're either going to get higher recall or higher precision, usually not both. And so this plot is a PR curve from a project that Suzanne and I worked on. It can actually vary quite a bit. So we plotted the confidence threshold in relation to precision and recall. And you can see that changing it from 0.61 to 0.64 had like a 10% difference in recall and precision, which is quite extreme. So you want to set this carefully for your data. And it's also going to depend on what you then use the object detector for, right? So you want to test it, if you're doing multi-object tracking, you want to test the detector confidence threshold in relation to your tracking performance. And so I'll just end this section by saying that this is not everything. There are many different task-specific metrics or hyperparameters that I haven't covered. And so you just kind of have to dig into them yourself, figure out which ones look like they matter for you, and try some values. Just remember these principles. Try to reduce the search space, look at your validation set performance, and avoid any obvious pitfalls. This is a cool, this is our fish counting project. This is a sonar video where we're detecting and tracking the fish as they cross the center line of the camera. So we're trying to count how many salmon are migrating upstream every year. So we use a YOLO detector and we tune the confidence threshold before putting it into a tracker. The tracker also has a few other hyperparameters that we tune. We just use a Kalman filter. We use a paper called SORT. That's like a Kalman filter plus IOU box association. Okay, technically we're over time. I'm gonna try to do this bonus section in like a couple minutes. Yeah. Okay. Sounds good. Okay, this is a common problem that a lot of people here have. You have imbalanced data and maybe you've got some performance metrics, like what do you do to make that better? So first of all, why is it hard? So it's kind of simple. You have a lot more training signal coming from the abundant classes. So when you calculate your loss, most of that loss is coming from the majority class. And so most of your model update is going in the direction of getting better on the majority class. It doesn't get rewarded very much for getting better on this minority class, right? And so there's a few techniques that people use. The bad news is that nothing really works that well. You can probably use these techniques to get a little bit of improvement, but don't expect imbalanced data to be solved. It's an active research area. Here are 3 common things that people do that might work for you. First is over or undersampling your data. So first I'll say that these ideas are probably somewhat common sense and you probably also had them yourself, right? Like if you want to make your majority class not a majority class anymore, just undersample it and now your data set's more balanced. Similarly, you can oversample the minority class. And so you can do this either physically on disk, like just copy your files or reduce the number of files in your training data set folder, or you could write a custom data loader to do it. That's more work, but maybe more flexible because you could change the sampling ratio more easily. So this would be the first thing to try. Just downsample your data into a new folder, train on that data and see what happens. Yeah.
Teams that don't have the thing you're interested in, obviously, talk about the number of pixels in the scene,
Yeah, so it's more complicated in segmentation for sure. Because in classification, you just have one thing per image, but that's not true for segmentation. So you could kind of try it both ways. If you think that you could downsample just based on whether or not the rare object is in the image, then you could do that. But if those objects are also really tiny, yeah. Yeah, so you could do that, exactly. You could just crop the image smaller. It's not ideal, but I think that's how you would try to do the undersampling in that case. Yeah. Okay, the other way that's a little bit equivalent to that, or it's a little bit equivalent to oversampling at least, is that you look at your loss and you upweight the loss of the rare classes. So you basically tell it manually, I care about the rare classes more, multiply the rare class loss by a factor of 2 or something. The nice thing is that PyTorch has this just built into a lot of loss functions. So you can just pass in, for example, if you're using a cross entropy loss, you just pass in a weight vector that has a value for each class. So this weight array is like the same length as the number of classes you have. For each class, you have a weight. So you can compute those based on the imbalance ratio. You can try a few different sort of common sense things. In practice, it's a bit less stable than just oversampling or undersampling. Because you might, so your data loading is random, like you're randomly selecting images for the batch. If you just happen to select a bunch of rare examples in this batch, and you've upweighted the loss by like a factor of 10, you might end up with a massive loss for that batch that could get your model sort of diverging, or even get like an infinite loss, which would be bad. It would kill your trading. So you just kind of have to try it. Just see what values work, see if it's causing problems, see how it does in relation to undersampling and oversampling. It's different. Yeah, so this would be at training time, how you're weighting the loss of your batch. Versus calibration is more at inference time, how you're weighting the prediction for each class. Yeah. Okay, the third option that's a bit controversial, we call it distribution aligned fine tuning, or a simpler version would be balanced fine tuning. So you first train a model on all your data, then you undersample it, and then you train for like one epoch on the undersampled version. Okay, people have shown that this improves results, but the key is that it improves results on a balanced test set. So you essentially are fine-tuning on the distribution of your test set, which gives you better results on that test set. But if your test set is also imbalanced, this probably is not going to do anything for you. Okay, and it's something to keep in mind because, you know, you might see some performance boost, but if you don't think that your data in the real world is going to be balanced, then this probably isn't going to do anything for you. It just sort of like unbiased or rebiases it toward a balanced class distribution a little bit at the end. And if this seems like it applies to you, there's a paper down here that I linked.
Like if you just couldn't get enough examples of something, you know, that's actually.
Exactly. Yeah, exactly. Yeah. Or if you happen to know, because you're an expert of in the species in some region, if you happen to know your test distribution somehow, you could just try to mimic that and fine tune this model to your test distribution. I think it's.
A really good example of like if you have a random sample of entertainment data from your actual application, then you can expect a random sample match distribution and you can train to it. But then the sooner that distribution.
Okay, that's all I got. Anybody have more questions?
Yeah, regarding this comparison of you could train your model on certain type of event. And you could say like, yeah, in nature, you picture on that.
Yeah.
But then you go to a certain habitat where all of a sudden you're very specific on your domain.
Right.
So what do you do?
Yeah, exactly. So that's something where you could use this like balanced fine tuning. Like if you happen to know that out in the real world, you're going to encounter that distribution, then you could sort of fine tune on it at the end. But if you don't know ahead of time. Yeah, exactly. So that's right. And this is always the challenge, right? You're trying to construct a validation set that's going to tell you something about how your model does. You're trying to construct a test set that's going to tell you something about how your model's going to do in the real world. That's kind of the best we can do toward understanding how it's going to do, right? The quality of the test set and how much it matches the real parameters of the world is going to determine how much of a generalization gap we're going to see when you actually deploy it. How surprised are you going to be? And if the real world distribution differs from your test and validation distributions, it's probably going to be, there's probably going to be a difference there. Yeah. So you decide you don't want to train anymore, you want to keep your model, or like for a given hyperparameter. Yeah, so what I do is I usually go through one parameter at a time, fix everything, test a few values for learning rate. Okay, you find the best one out of the 3 that you tried, and now you just keep that. Keep that learning rate for your future experiments. Then move on to image size. Try a few different sizes, pick the best one. Now you have learning rate and image size fixed, and now you move on to the next one. And I would just do that for, you know, the most important 4 or 5 different parameters, and then you have pretty decent settings, and then you can kind of just set it and forget it.
This might be his own misconception, but I was really impressed with like the model architecture size. The image size is pretty thick. I didn't like that.
Yeah, that used to be the case. People have come up with nice ways of making them more flexible now. But in general, like if you pre-train on some image size and then you want to fine tune it on a different image size, that's harder to do just because it's learned features specific to the resolution. But most designs now are flexible to different input sizes.